Have you ever really thought about how a medicine knows exactly where to go once it's in your body? Well, it's not magic. It's all about these tiny little molecular locks that are on every single one of your cells. And today, we're going to go find the keys.
I mean, really think about it. You pop a pill for a headache, right? And somehow it doesn't just, I don't know, accidentally tell your pinky toe to stop hurting. How in the world does it know its specific target? Well, the answer is this amazing, super precise communication system that's happening inside you right this very second.
All right, so the hero of our story, the little molecule that makes all this targeted action possible, is called a receptor. And let me tell you, if you can wrap your head around this one concept, you've basically unlocked the secret to how modern medicine really works. Okay, let's bring this out of the textbook and into the real world. Picture this. A man is having a really bad asthma attack. His airways are closing up. A doctor injects him with epinephrine and boom, minutes later, he's breathing again. That epinephrine didn't just stumble around his body hoping for the best. Nope, it made a beeline for the exact receptors in his lungs that signal those muscles to relax. That right there is precision medicine in action. So, what exactly is a receptor? Well, at its heart, it's a protein that acts like a super specific lock. It can be on the outside of a cell or even on the inside, and it just sits there patiently waiting for the one perfect chemical key to show up, fit inside, and tell it what to do next. And these little molecular locks, they've got three huge jobs. First, they're the ones that determine how much of a drug you actually need to get an effect. Second, their unique shape is what makes drugs so selective. It's why only the right key fits. And third, they are literally the on or off switches that drugs either flip on or jam off. Okay, so if receptors are the locks, it's pretty obvious that drugs are the keys. But, not all keys are created equal, right? Some are made to open the lock, and others, well, others are designed to jam it up completely. And that brings us to the two big players in this game, agonists and antagonists. Think of agonists as the master keys. They fit the lock perfectly, they turn it, and they switch on a response in the cell. Then you have antagonists. These are the jammer keys. They slide right into the lock, but they don't turn. They just sit there, gumming up the works and blocking the real master keys from getting in. So, let's zoom in on those agonists, the on switches. They actually come in two flavors, full and partial. A full agonist, that's your perfectly cut, factory-fresh key. It turns the lock without any trouble and gives you the full 100% maximum effect. But a partial agonist, that's more like a worn-out old key. Yeah, it'll still open the lock, but maybe it's a little sticky, it doesn't turn as smoothly, and you only get a weaker response. At our antagonists, the blockers, well, they do exactly what you'd think. They just camp out in the receptor. They don't activate anything, they just occupy the space. And by doing that, they stop your body's own natural keys, or any other agonist drugs, from getting in and turning the lock. Okay, now this is where it gets really cool. It turns out there are two different ways to jam a lock. On the left, you've got what's called a competitive antagonist. This is basically a numbers game. If you have enough of the right keys, the agonists, you can eventually push the jammer key out of the way. But on the right, that's a non-competitive antagonist. This thing binds so tightly, it's like someone put superglue on the wrong key and stuck it in the lock. It doesn't matter how many master keys you throw at it, you are just not going to get that full effect anymore. All right, so we get it. Locks, keys, makes sense. But how do we actually measure how well a particular key works, right? Well, in the world of pharmacology, it all boils down to two really important words, potency and efficacy. Now, these two terms trip people up all the time, but it's actually pretty simple. Potency is just about the amount of drug you need to get a result. If a drug is super potent, you only need a tiny bit. Efficacy, that's different. Efficacy is all about the maximum possible effect the drug can produce. It's the drug's raw power. And here's the key takeaway. They are not the same thing. You can have a really potent drug that doesn't actually do very much, and you can have a less potent drug that's incredibly effective once you get the dose right. Okay, so getting an effect is great, but that's only half the story, isn't it? We also need to know if a drug is safe. And that's where something called the therapeutic index comes into play. It's basically a simple ratio that tells us our margin of safety, how much wiggle room we have. And this graph just lays it out perfectly. See the blue curve? That's the sweet spot where the drug is doing its job. Now look at the red curve. That's where it starts to become toxic. The bigger the gap between blue and red, the safer the drug is. You want a really wide gap, a big margin for error, so that tiny little differences in the dose don't accidentally push you into the danger zone. Okay, we've got the key in the lock, we've turned it. So what happens now? I mean, how does that one little action on the outside of a cell cause a huge change on the inside? Well, that's all thanks to something called signaling mechanisms.
It turns out there are a bunch of different ways a cell can get the message. Think of it like different ways to wire a doorbell. We're going to do a quick flyby of some of the most important ways this signal gets from the outside in.
So first up, you've got these little lipid-soluble drugs. They're so slippery they don't even need a knock. They just slide right through the cell membrane and find a receptor that's just hanging out inside. A lot of the time, they go straight to the cell's command center, the nucleus, and start changing which genes are turned on or off. It's a bit slower, but man, is it powerful. All right, method number 2, you've got these receptors that are a 2-for-1 deal. They're also an enzyme. The part that's on the outside of the cell snags the drug, and that instantly flips a switch that activates the enzyme part on the inside. Insulin is a perfect example. It hits the receptor, which tells the enzyme inside to get busy and start processing sugar. Then, you have receptors that are even more direct. The receptor is the channel. It's like a gatekeeper. When the right drug comes along and binds to it, the gate just swings open and ions come flooding in or out. This changes the cell's electrical charge like that, in a split second. This is absolutely critical for how our nerves communicate. And finally, we've got the most common system of all, which uses something called G proteins. In this setup, the receptor is kind of like a manager. It gets the message from the drug, but it doesn't do the work itself. Instead, it delegates. It passes the order to a little middle manager called a G protein. That G protein then creates what's called a second messenger. Think of it like an internal memo that blasts the message all over the inside of the cell. It's a great way to amplify a tiny signal into a huge response. But here's the thing, and this is probably the most fascinating part of the whole story. Our bodies aren't just static machines. Those locks on our cells, they're not permanent fixtures. They can and they do change, especially when we keep hitting them with the same drug over and over. So imagine a cell is just getting bombarded by an agonist. The doorbell is ringing off the hook, nonstop. What does the cell do? It does something really smart. It starts pulling those doorbells, the receptors, off the surface and hiding them inside. This is called downregulation, and it's the real molecular reason behind drug tolerance. It's why after a while, you might need more of a drug to get that same old effect. And you guessed it, the exact opposite happens too. If you're constantly blocking a receptor with an antagonist, the cell gets worried. It thinks, hey, I'm not getting any messages. So it starts building and installing more receptors, trying to catch a signal. This is called upregulation, and it's why stopping a blocker drug suddenly can make the cell go into overdrive, becoming hypersensitive. So what you see is that the relationship between a drug and a receptor isn't some simple one-time event. It's a dance. A constantly changing, dynamic interaction. Our bodies are just unbelievably adaptive, which leaves us with a really big question for the future of medicine. How can we start designing drugs that are as smart and as adaptive as we are?